This is part 5 of the module 9 lecture. In this, we're going to start to talk about comparing the means of the two independent populations when the variances are equal but unknown. And this is covered in section 10.2 of the textbook. So again, using our flow diagram that we had before, so you see we're comparing two independent populations. We have already tested whether the variances are equal or not. And now we're considering the case where the result of comparing the two variances shows that they are statistically equal. So we're going to look at how to compare the means of two independent populations when the variances are equal but unknown. All right, the test procedure is going to be the same that we have been using. The difference is going to be on how we state the null hypothesis, how we select the distribution to use, and we calculate the test statistic. From there on, the procedure is practically the same. All right, so the first problem we encounter is how do we state the hypothesis when we're comparing the means of two independent populations. Well, the intuitive way to do it is to say, well, the null hypothesis for a two-tail test is that the two means are the same, versus the alternative hypothesis that the two means are different. Well, because we cannot construct two separate probabilities, or rather, we cannot use the two probability distributions to figure out whether they are equal or not. So the way we do it is by taking the difference of the two means and determining if that difference is 0 or not 0. So in the case of a two-tailed test, for the null hypothesis, we said the mean of the first population minus the mean of the second population must be equal to 0 if they are equal. And that same difference, if they are not equal, must be different from 0. Now, I wanted to call your attention to this note. Sometimes the difference is not assumed to be equal to 0. It's being assumed equal to some other quantity. For example, let's say you want to show that the mean of the first population is 3 times bigger than the mean of the first population. Well, in that case, this will not be equal to 0. It will be equal to 3. So you need to be very careful when you're reading the problem that you're solving. And when you write in the hypothesis, you need to realize whether the difference is equal to 0 or equal to some other quantity. And the same applies for the other directions of the test. All right, so if we have a left-tailed test, in here we're looking at the first mean being smaller than the second mean under the alternative hypothesis. And under the null hypothesis, the first mean will be larger or equal than the first mean. So that in terms of differences, under the null hypothesis, we have the first mean minus the second mean will be equal or larger than 0. That means it's positive, implying that mu1 is bigger than mu2. And under the alternative hypothesis, you have that mu1 minus mu2 is less than 0, meaning that is negative, because mu2 is bigger than mu1, as stated in the alternative hypothesis here. Now, if you have a right-tailed test, again, under the alternative hypothesis, you want to show that the first mean is larger than the second mean, and the assumption under the null hypothesis is the first mean is less than or equal than the second mean. In terms of differences, then under the null hypothesis, you have mu1 minus mu2, and that difference will be less than or equal to 0. So that will be 0 or negative, meaning that mu2 is bigger than mu1. Under the alternative hypothesis, now you have that mu1 minus mu2 will be bigger than 0, meaning that it's positive, implying that mu1 is bigger than mu2, and that's what you have on the alternative hypothesis for a right-tailed test. Again, you need to read the problem carefully and decide what kind of hypothesis, what kind of hypothesis you have and what the direction of the test is. All right, so now how do we find this distribution of differences so that we can carry out this comparison? So we're going to use the difference of the sample means to estimate the difference of the population means. So if we have two random variables, x1 and x2, and they're normally distributed with mean and variances mu1 and sigma 1 square and mu2 and sigma 1 2 square, then the distribution of the difference of those two random variables will have a mean of mu1 minus mu2 and a variance of sigma 1 square plus sigma 2 square. That's in terms of just the random variables. Now the next question is, well, what is the sampling distribution for the means from each of these random variables? Well, as we learned back in module 7, that then the sampling distributions of each of these random variables for their means, the means of those sampling distributions will be mu1 and mu2, and their standard deviation will be mu1 over, sigma 1 divided by n1 and sigma 2 divided by n2. And by the central limit theorem, if we're sampling from normal populations, well, the sampling distributions will be normal. Or if we have a sample size of at least 30, then the sampling distributions are normally distributed. So now the question is, well, what is the distribution of the sampling distribution of the difference of these two sample averages? Well, it will be normally distributed with a mean of mu1 minus mu2, and the standard deviation of that sampling distribution of the difference of the sample means will now be the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2, which is the same as this, except that now we're dealing with the sampling distribution. Now, in the case that we're dealing with right now is that the two variances are equal. The two population variances are equal. Therefore, we have a common variance sigma squared. And under that assumption, then the sampling distribution of the difference of the averages will be used the mean, the difference of the two population means, but the standard deviation now it be sigma times the square root of the 1 over n1 plus 1 over n2. We're taking the sigma squared out as a common factor and taking it out of that square root. So now what we have then is we have two populations that are normally distributed with equal variances, and now we have a single sampling distribution of the difference of the averages. And now we have that the mean is mu1 minus mu2, and the standard deviation is sigma times the square root of the inverse of the sample sizes. So with that knowledge then, we say, well, but this common variance, sigma, is not known. So what do we do? Well, we replace it with the estimator of the variance. But in this case, we have two estimators, the estimator from the first sample and the estimator from the second sample. And both of them estimate the same thing, sigma squared. So what do we do when we have two estimators that estimate the same thing? Well, we combine them into a single estimator. And in here, we call this estimator the pool variance. And as you see, is the degrees of freedom times the first variance plus the degrees of freedom times the second variance divided by n1 plus n2 minus 2. So this is called the pooled variance. And so this unknown common variance, we're going to replace it with this estimate, the pooled variance. So you remember from module 8 and module 7, every time we replace a variance with a sample variance, well, we end up using a t-distribution. And that's exactly what we're going to have here. So the test statistic for equal but unknown variances now is defined as this. So remember, we're using the estimator, the difference of the sample means, minus the assumed difference of means from the null hypothesis. And most of the time that will be 0, but sometimes might not be 0. And then we divide it by the square root where I pull of the pooled variance times the inverse of the sample sizes. Now, this test statistics follows a t-distribution with degrees of freedom of n minus 1 plus n minus 2 minus 1, which is the sum of the two degrees of freedom, or we just simplify as n1 plus n2 minus 2. And this is true if both samples consist of independent observations. The sampling distribution of x1 minus x2 bar is normal. and the pool variances the pool variance replaces the common variances. And remember, the sampling distribution of the difference of means will be normal if either we're sampling from two normal populations or the two sample sizes are large. All right, so now this is the test statistic. This is now how we're going to find the t-distribution to use with these degrees of freedom. So the next question is, well, how do we proceed to make a decision about the null hypothesis if we want to use the critical value? Well, the same as before. The only difference, and we're going to use table 5 as we learned in the previous module, but in this case, the degrees of freedom will be n1 plus n2 minus 2. And again, if you have a left tail test, well, the rejection region is to the left and is defined by the value of the significance level. And so the critical value, we're going to find it in table 5 with alpha, and then we use the symmetry of the distribution to find the low value. If you have a right tail test, well, now we're looking on to the right of some critical value, and we're going to use alpha to find it, and that comes directly from table 5. If we have a two-tail test, then again we use table 5, and we divide alpha by 2 to find the two critical values that define the two rejection regions. All right, if we want to use the p-value approach, again, the rule is the same as before. We reject, before I forget, the rule for using the critical value is the same as before. If the observed value of the calculated statistic falls in the rejection regions, in either of the rejection regions, then we reject the null hypothesis. So the rule is the same. In the case of the p-value, we use the same rule. If the p-value is smaller than alpha, the significance level, we reject the null hypothesis. If the p-value is larger than the significance level, we do not reject the null hypothesis. And as before, if you like to find the exact p-value, remember that table 5 only gives you approximate p-values within the actual p-value is. But if you want to find the exact p-value, you can use these Excel formulas here. All right, the last thing is now we're going to also need to calculate the confidence interval for the difference of the two population means. And that confidence interval is now given using the point estimate of the difference of the two means minus the t value found by using alpha divided by 2 and the degrees of freedom of n1 plus n2 minus 2. And we use this new expression of the standard error, which is the pooled variance times the sum of the inverse of the sample sizes. And again, this critical value is found from table 5. All right, so now we're going to look at an example, and we're going to apply everything that we learned to solve that example, where we compare the two means from two independent populations that have equal variances, but the variances are unknown. So in the next recording, we'll address, we will solve a problem.